Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic is noise in communication systems. Noise in communication systems can be attributed to external sources as discussed in Module 001 or from components constituting the subsystems making up the entire communication system itself. The latter is known as internally generated noise, and this module will only consider this type of noise. Internally generated noise arises from the random motion of charged carriers within the system component and can be categorized as flicker noise, short noise, and thermal noise. Noise is due to the motion of charge carriers through a junction, such as the junction between P and N-type materials of a semiconductor diode. Flicker noise, on the other hand, is characterized by increasing intensity with decreasing frequency and is sometimes referred to as 1/F noise. Thermal noise, also known as Johnson noise, is due to the random motion of charge carriers within resistive materials and is often treated in terms of noise figure F and noise temperature T. We will be limiting ourselves to the treatment of thermal noise in this model. The noise figure of a device or subsystem is defined as the ratio of signal to noise power ratio at the input of the device to the signal to noise power ratio at the output, as seen in equation 1, where measurements are made at the standard temperature of T0 equals 290 Kelvin, and SI over NI is equal to signal to noise power ratio at input. S0 over N0 is equal to signal to noise power ratio at output. NI is the available noise power at input. N0 equals available noise power at output, and G is the system power gain, which is given as S0 over SI. If we consider a typical communication system as shown in Fig 1, you see that you have the input, you now have the input resistance, the output resistance, the internal resistance of the source given as Rs, and the load resistance given as Rg. For maximum power to be transferred, there must be matched conditions. That is, Rs must be equal to Ri and R0 will be equal to Rg. The mean square thermal noise voltage produced by Rs is given as V RMS squared is equal to 4 kT BRS. Equation 2, where K is equal to the Boltzmann constant given as 1.38 times 10 raised to power minus 3 Joule per Kelvin. T is absolute temperature in Kelvin, and B is equal to bandwidth of operations. Available noise power across Rs will now be given as PA equals half VRMS squared all over Rs, which is VRMS over 4Rs, which is equal to 4 kTBRS over 4Rs, giving KTB, which is referred to as equation 3. This implies that the available noise power is independent of the source resistance if T is equal to T0 equal to 290 Kelvin. From equation 1, the noise figure of a device can be viewed as a measure of the degradation in signal to noise ratio imposed by the device or subsystem under consideration. Better still, it can be viewed as a measure of the increase in output noise power over input noise power due to the internal noise added by the device under consideration. In equation form, the noise figure F is given as KT naught BG plus delta N all over KT naught BG, which is equal to 1 plus delta N over KT naught BG, equation 4, where G is the available power gain of the subsystem and delta N is the internally generated noise power of the subsystem. Now, consider a typical communications receiver subsystem in equivalent circuit form cascaded as shown in Fig 2. You have at the input the absolute temperature, which is equal to T naught. You have the input temperature input to the phase stage, which is the noiseless RF stage with gain G1. The next noiseless down converter gain G2. The next model noiseless IF stage with gain G3, as shown in Fig 2. Now, let G1, G2 up to Gn be their respective available power gains, and delta N1, delta N2 up to delta Nn be their internally generated noise powers. Considering the first two cascades, their contributions to the output noise power is given as KT naught B G1 G2, which is equal to the available noise power at the input amplifier by the cascade and appearing at the output. Delta N1 G2 equals the internally generated noise of the first subsystem of the cascade amplified by the second subsystem and appearing at the output of the cascade. Delta N3 equals the internally generated noise of the second subsystem of the cascade and appearing at its output. The overall noise figure of the first of the cascade from equation 4 is the total noise power appearing at its output divided by the available noise power at its input amplified by the system. So that will give F equals KT naught B G1 G2 plus delta N1 G2 plus delta N2 all over KT naught B G1 G2. If you divide further, you get equation 5, which says that the total noise figure will be equal to F1 plus F2 minus 1 over G1. Therefore, for n cascaded subsystems, it will give F equal to F1 plus F2 minus 1 over G1 plus F3 minus 1 over G1 G2 until you get to the last cascade, which will give Fn minus 1 over G1 G2 up to Gn minus 1 as equation 6. Equation 6 is known as the phase formula. This shows that it is important that the first stage in the cascade have a low noise figure and a large gain for a low overall noise figure. Since F is dimensionless, it follows from equation 4 that the quantity delta N over KBG has the dimensions of temperature. Accordingly, the effective noise temperature of a device or subsystem is now defined as TE equals delta N over KBG, equation 7. This allows the noise figure to be written as F equal to 1 plus TE over T naught, which when solved for TE gives TE equals F minus 1 into T naught. For cascaded subsystems with noise temperatures T1, T2, Tn, and available power gains G1, G2, Gn, the effective noise temperature of the cascade is given as Te equals T1 plus T2 over G1 plus T3 over G1, G2 plus until you get to Tn over G1, G2 up to Gn minus 1, equation 10. Note, it is important that the receiver factors in the effects of noise generated by the antenna or intercepted by the antenna as a result of hot bodies within its field of view, such as the sun, stars, and other heavenly bodies. If we denote this antenna temperature as Ta, then the system noise temperature T6 will be given as T6 equals Ta plus Te, equation 11. It is also very important to make sure that the first stage of any cascaded subsystem is not an attenuator, for the noise figure of an attenuator of loss factor L is equal to 1 over G and is simply given as F attenuator is equal to loss, equation 12. Thank you for listening. Please like, share, and subscribe. Drop your comments, questions, or topic you want me to lecture on in the comments section.